Welcome to this lecture from our course on thermal building physics, the lecture on transient heat transmission, and rather the part of the lecture where we talk about analytical solutions for finite and infinite bodies, as I'll explain to you soon. But it's about transient calculations of temperature profiles in materials or walls in principle in building structures, of course. So let's see how it goes. This comes as a solution to our general heat conduction equation, this parabolic differential equation, where we find the temperature as function of time and location x, where we are in the depth of our material. So we need this property of our material, also the thermal diffusivity. Question is how to solve this equation. So it can be sometimes a little bit difficult or involving to do so. So therefore, we have in our course a problem-solving strategy where sometimes we are covering the very simple cases we call lumped analysis, which is not part of the lecture here, this part of the lecture. Here we talk about the analytical solutions in a certain number of cases that we have to identify and divide between when we should find our proper formulas. So this is what I'll go through and find cases where we can in certain situations find formulas that gives us the temperature profiles within the materials. In certain cases, as in the end, we also have chart solutions where we can read the results rather than calculate them with our formulas. So let's get started with it. And to get started, we have to make a division of what kind of bodies or materials we are analyzing. And the first one is a semi-infinite body. I cannot explain exactly what is a semi-infinite body. I have to do it indirectly by taking a finite body. So assume this is our wall, which has a left-hand surface and a right-hand surface. This is a normal finite body. But a semi-infinite body is one that has only one surface and then projects infinitely in the other direction, here going on the right as such. So that would be a semi-infinite body. That's the easiest solutions we have for those. So that's why we start with this superficial material, the semi-infinite body. We take that for our case of having a fixed surface temperature on the surface of our material. And we have to go through a certain number of cases. So if you follow me over here to the table here, then we are now in the semi-infinite and we have a fixed surface temperature that will curve. So we will go through cases here in the table here. I'll go back to show you on the PowerPoint slide here the solution, but here's our case. So we are going to find the temperature profiles as it develops into the material after initially we have the initial temperature, and suddenly at time zero it drops to the surface temperature up here. So those are curves for temperatures that we will have formulas for. And here is the formula. It tells us the temperature at location x and t in our body, in our material, how it depends or varies from the surface temperature and the initial temperature using the error function, and then we should insert the location x and the time t as such. We can also sometimes use the complementary error function, which is just 1 minus the error function. Similar formula, more or less, looks a little bit differently down in the denominator. So that's it. And then we can calculate, you just have to insert. The next case for which we have a solution, it's the case where we have a convective heat transfer coefficient at the surface of our material. So this I'll put across in the table here. That means that it's not the surface temperature, but the air temperature next to our material that suddenly changes to another fixed value. And in that case, well then, here is a plot of it. So you can see that we have also, first of all, the heat to be transmitted to the surface of the material before it comes into the material. So it's a little bit slower, the process, compared to the case if it were the surface temperature that changed initially. Here's a formula. Starts the same as the formula we had before when we talked about surface temperature changes, but then how much slower it goes is all what we deduct here. So you have to use an exponential formula and a complementary error function, but otherwise it's a matter of inserting them. In a few cases you have to be careful. For large arguments, this tends to infinity, and this tends to 0, and you have to be careful with what happens when you multiply a very large value with something which is very close to 0. But there are mathematical tricks how to cope with that. So that was that case. The next case is that we have, again, a semi-infinite body, and then at the surface of material, it's a heat flux that is impinging onto the surface, like it could be solar gain that you have on the surface. For such a case, I'll just put a cross in our table here over here, of course, so we can see that we are progressing. For that case, then we have a formula that tells us, again, temperature profiles in our material. And here is the formula, a rather simple formula, but again, you're going to use the complementary error function. But inserting to find arguments, you have to insert the location x and the time t again. That's possible. The trick is only to identify the right case that you're dealing with. And now we have covered cases for those semi-infinite bodies. A little bit superficial, but can, in certain cases, or for small times after the exposure, they can be adopted, even in the case that in the real world, we have a finite material. In the beginning material, if you have an exposure on the surface, in the beginning the material doesn't know if it's infinite in one direction or if it really is a finite sized material. So then the temperature profiles initially will always work the same. So semi-infinite solutions can be also practically applicable for small times. Now, let's go then to what is more realistic even then. It's finite bodies, so materials which have a certain finite thickness only. And there are solutions only as we progress. The more realistic the cases are, mathematically they are a little bit more involving. So now we are here, in this case, with a finite body and a fixed surface temperature on the surfaces of our material. So here's our material, two surfaces, suddenly that temperature changes. And here's a solution. So the involvement is, and now it's an infinite sum that you have to calculate. So you have to make quite some calculations, add them up. But we're fortunate that very often when you try, they tend rather soon to become very small. So you need perhaps only a few first terms in that summation when you try to calculate it. So that's possible also to make such a solution there. Then you can also plot it, or you can also read from the chart, depending on the time with the Fourier number. Then you can read the values as they are for the temperature inside of our body after a change has occurred. We start up right here on the top, and then at the surface it drops to zero initially. That's for this case that is plotted here. The last case I will talk about today is a case, again, with a finite body, but now with a convective heat transfer coefficient. So that means, if I may hold my material again, that it's not the surface temperature of the finite material, but it's the air next to our material that suddenly changes to another value, and how then would be the temperature profiles within my material. So again, another formula that you have to identify to find. But the trick here is that it uses some coefficients zeta n. So that is zeta 1, zeta 2, zeta 3, and so forth, that you have to identify those coefficients. And those coefficients, they are the roots of this equation down here. Cotangents to zeta is equal to zeta over the BO number for our problem. The rest is to insert the geometry, so the location x where we are, and x is the distance that you are away from the center of our material. L is the characteristic length of our material, which for a double-sided material, or double-sided exposure of a material, is half of the thickness of the material. So L is half the thickness. So that's how you can insert, and you can make calculations for that. Again, with an infinite sum, but they tend rather soon to a small number. But if you want also you not to calculate, then you can make a chart solution. And here's a chart that tells you what is the temperature in the center of our material as we had it. When you insert with the correct BO number and the time, the Fourier number, you insert down here in the abscissor axis. Then you can find the center temperature. If you were not interested in the center temperature, but you needed a temperature somewhere away from the center, then there's another chart where you insert, you find the right line for x over L. So x is the distance away from the center compared to L. So for that, then you can correct, or you can add on top of having known the center temperature, which is part of what is read over here, then you can find the temperature at that other location in which you are. So that is what charts can be used for, with whatever accuracy with which you can read results from such charts And if you're not satisfied with that, well, then you can always use the formulas that I've shown you. So for me, for today, for this lecture, that's all. I hope you really enjoyed it and that you can use those formulas and results. Thank you for now.